Okay, let's pick up where we left off with stereochemistry. Any questions about stereochemistry thus far? Okay, guys, I think we're here. Identify any chiral carbons in the compounds below. Does this compound have any chiral carbons? No, no chiral carbons. This compound's not chiral. The mirror image is the same thing. How about this compound? Any chiral carbons? No chiral carbons. The mirror image is the same thing. Not chiral. How about this guy? Any chiral carbons? Yes, this compound here is chiral. Okay, that means it has two orientations or projections that it can have. We can draw these. Draw this forward, and we can also draw it back. And those are enantiomers. RS. Anybody have these? R or S? What'd you get? First one? Yes, R. And I'll bet you a steak dinner that one's S. How do we do? Any questions about those? No? Optical activity. A 50-50 mix of enantiomers gives no net rotation of pp light. Okay? You have an equal mixture of enantiomers, no net rotation. That's mainly because, actually one enantiomer is rotating the light one way, but you have 50% equal amount of the other enantiomer rotates it back the other way, and you get back to zero. So there's no net rotation. You can only see the net rotation. It's called a racemic mixture. No net rotation of pp light. 100-0 mix is also easy. Well, because that's going to be a literature value. And we've given that for like 2-butanol before. What was that, plus or minus 13.5, I believe? That comes from literature. Or you have to determine it yourself. If you have a pure compound, a pure enantiomer, then the value is the value. 50-50 mix is easy. 0 is the value. Racemic mixture. But what about mixtures that are not 50-50? Or 100-0? For example, what if you had 90-10? 90% one enantiomer and 10% of the other. What would its rotation be? That's what this is talking about down here. Please be looking at that. See what type of questions you have and make sure you're able to do those types of things down there. Any questions about those that there thus far? Let's move down here to Fischer projections. Assign RS to each compound below. How do we do on this one? Anybody get this one? RS. S? Who says S? How did you get S? Let's see. S? I think it might be S. Key thing here is that the H is not in the plane. I'm sorry, it is in the plane, not back. Low priority group here is H, right? High priority group 1, chlorine 2, carbon 3. I mean, this is counterclockwise, but the low priority group is not in the back. did you get S? You didn't just do it like that, did it, get S? Because you did, it's just, yeah.
Can you look at the side? Go ahead and look at the side.
You got a 50-50 chance, because it's just, if the low priority group was in the back, we can say this is S. If it was in the front, we could just do what? Reverse it. It would be R. What do you do with it in the plane? We need to draw a Fischer projection. Okay? Draw a Fischer projection. Or should we do this first? Yes, we should do this first. Fischer projection. Okay, a Fischer projection is where you show a chiral center, typically chiral carbon, with a crosshair. All right? If we just draw a crosshair like this means something in chemistry land. This means that the things on the side are actually coming towards you. Equal, we'll use this right here as a center carbon. The things on the sides are actually coming towards you. So like cat whiskers. Or a bow tie. A little bit. The things at the top and bottom are actually going back. Okay? So whenever you see the crosshairs with organic compounds, it's called a Fischer projection, and it means this. Okay? Fischer, spelled with a C. All right. We have a carbon with 4 bonds connected. Now, in this view, everything has got a forward or back, because let's look at this. Let's take a compound. Let's take this compound here. Black straight up. Nothing, straight up. H is gray in the plane. So those two are on the board, flat. Chlorine red coming out. Bromine green going back. There it is on the board as drawn. Everybody agree? Okay. But we could draw this on the board other ways. For example, what if we drew it like that on the board? Two things to the side from your view. And look, they're to the side, but are they going back or forward? Back behind the boards or towards you? They're to the sides, but they're also towards you. To the sides, but also towards you. See how this is? Now look at the things that are going up and down. That's going up, but is it going straight up? Actually, no, is it? It's actually going up and back. Just like the gray is going down and back. So right here, nothing is in the plane. 2 are forward and 2 are back. And this is a Fischer projection. Just like this. Things on the side coming forward, top and bottom going back. And whenever we just draw it like this though. So whenever you see the crosshair, it's really not flat on the board. You have to know that this implies that the things on the sides are forward, top and bottom back. All right. This Fischer projection, we only have 1 chiral carbon, so we only need 1 carbon in our Fischer projection. When we see 2, we'll understand what that means, or what the difference would be. How do we get this into this view? Well, we can just look at it that way. The things that are projected here are the things that are best to be on the sides. And if we stand over here and look through there, we're going to see this Fischer projection. The compound is on the board like this. Everybody agree it's drawn like that on the board? Okay. If I stand over here, the little guy's over here looking, just like, okay, here I am looking, what do I see? First off, I want to come down a little bit and look through here. That's why I'm leaning a little bit. What do I see? I'm going to turn and let you see what I see. What do I see? I see the Fischer projection. Things on the sides coming out, top and bottom, going back. You got to look at it so you see it. If I stand over here, okay? Now let's draw it. Act like you're over here. By the way, if you have your paper, see, I can't turn the board. If I could, I'd turn this board and let you see what I'm seeing. If I got it on the paper, there it is on the paper, I could turn it and look down. Okay, well, I'm over here. So let's do this. What do I see? First off, I see a carbon that has 4 different things attached. I can have my Fischer projection. There's the carbon with 4 different things attached. Okay, what do I see going straight up on the carbon? A methyl. It's going straight up. Let's just clarify that that's a methyl. What's going straight down to my feet? Here's the ground. What's going down towards the ground off of this carbon? The hydrogen. It's going down. Yes, it's also going back compared to me over here, but it's going down. But that's what that means. It's also going back. Okay, here it is on the board. Okay, if I stand like this eventually is going to hit the ground. Yes, it's going away from me, but it's going down. Okay, what's coming to my right? The red here. Chlorine is red. Chlorine. Okay, if I'm over here, chlorine's coming this way, that's to my right. I'm just drawing what I'm see, this is what I see if I stand over there. Now you guys can see it. Chlorine's on the right. And the bromine, here it's going back. But if you can see what I see, you would see that it's coming to my left. Right? This is it in a Fischer projection. And when we see this, we know that the chlorine and the bromine are really coming forward. Right? There it is. Aren't they really coming forward? And the methyl, here it is on the board now. That's what that's supposed to mean. This is a different view, called a Fischer projection. The different view allows us to look at it easier sometimes. And you just have to know how to do a different view, called a Fischer. This is just called a good old standard perspective drawing with the dashed in bold. Fischer projection now, with something implied. The stereochemistry is implied. Okay, now let's do R and S. Bromine's 1, chlorine's 2, carbon's 3. 1, 2, 3, counterclockwise. How's the H? Is it forward or back? Well, it's going straight down, and straight down is back. So with the H is back now. With the H back, what do we have? S. It's much easier to see. We really did 2 steps here. We redrew it with the H more defined. Then we did a separate thing of we determined R or S. Determining R and S here is difficult because the H is not in the plane. Putting in a Fischer projection is a first very important step here, in my opinion. Thus my recommendation to you if you want to do this correctly more often than not. Fischer projection. Okay, let's put this guy in a Fischer projection. What is that over there? Can we tell anything related to the perspective drawings? Look like they're mirroring each other, aren't they? Are those mirror images?
Yes.
Well, if you got a chiral carbon, and if this is S, check, it is, chiral and it's S, then the mirror image is going to be what? Yeah, bet you a straight gun it's R. I bet you $100 million it's R. So the mirror image of S is R. Just like the mirror image of my right hand, mirror me. I'm holding up my right hand, you're holding up your, how's that? Because the mirror image of right hand is left hand. Fischer projection, how would we do it? I would stand over here and look through here. So the things that are projected here are going to be on your side, and you're looking, they're coming towards you, which is what this means. But you're also going to look right between them. Like right here. If you look at that dot, you're looking right between these two things on the side that are coming towards you. So let's look at this at the carbon with the two things on the side coming towards us. We've got to stand over here. We have to stand over here. What's on the side coming towards you guys? Which is my left if I'm over here? The chlorine. And the bromine is on the right. And straight up is the methyl, and straight down is the H. And this is the Fischer projection of the other molecule. Look at your fissures. Do the fissures look like they're mirroring each other? Yeah, fissures. You can see. And if you do this, bromine's 1, chlorine's 2, carbon's 3. What is this, clockwise? How's the H, forward or back? Back. So with the low priority group back, we have clockwise, R. These are Fischer projections. Questions? That's just one carbon. Certainly can do Fischer with just one carbon. Very important. Very useful. I'm having trouble seeing it here. Put in the Fischer projection. I recommend you do that because then it will be much easier to see in a lot of cases and future things we do. Learn how to do Fischer projection. You might wonder why Fischer projections were ever developed. And someone said, you know what, I have difficulty looking at this. I've already turned. The original perspective, I have difficulty looking at it. It's easier if I do it like this. I'm going to draw it like this. And when I do this, this is, well, it's tetrahedral, so we know it's not all flat on the board. So we have to assume that, you know, these are forward. And when I draw it like that, it's much easier to see. Yeah, I agree. Let's give it a name. Let's call it a Fischer projection. Okay, compounds with more than one chiral carbon. Moving on. Any questions? Any questions? Guys, as you go up in your courses, there's going to be more expectations of you just like, hi, any questions? No questions? Okay, let's have a test. Proactive. Okay? All right? So I do that a little bit here. And when you get to medical school, they're going to be doing this. All right? Compounds with more than one carbon. Here we go. Compounds with more than one chiral carbon. How many chiral carbons does this compound have? Yes, you all know what a chiral carbon is? Can identify them? There's 2. How many stereoisomers are possible for this compound? Previous compounds we worked with had 1. Okay? The mirror image is different. There's two stereoisomers called enantiomers. What about if we have 2? How many stereoisomers? There's a little formula. Number of stereoisomers possible. Maximum number, because it could be less, equals 2 to the n power. Where n equals number of stereogenic sites. A stereogenic site is a site that gives rise to stereochemistry. Because of that site, there's stereochemistry. Because this is chiral, we have some stereochemistry. We can have two different configurations, RS, about that carbon. So the way that is bonded, it's a stereogenic site. You got two stereogenic sites. So what is 2 to the n equal for this compound? 2 to the 2 is 4. Okay? That's the maximum number. Sometimes you may have less for certain reasons. But here it's 4. There's 4 stereoisomers possible. Now, what other type of stereogenic site have we seen? Alkenes. Alkenes may or may not be stereogenic. Not all alkenes. On the quiz, 3 out of the 4 I showed you were stereogenic, but there was one that was not. Now the alkene, the entire alkene is stereogenic, possibly. It's a site. The site consists of 2 carbons, but it's one site. Again, but not all alkenes are stereogenic. Right? But if we had a stereogenic alkene, such as this here, is that alkene stereogenic? Yes. Because you can have either cis or trans version of this. The way this is, there's stereochemistry there as well. Stereogenic. Cis or trans. One stereogenic site, 2 to the 1 would equal what? 2 to the 1 equals 2. There's 2 stereoisomers possible for that. They're called cis and trans. As drawn, it's trans, but we could also have the chlorine cis. Okay? So chiral carbon is a stereogenic site, and alkene is sometimes a stereogenic site. You have to know when. Okay, let's draw the stereoisomers here. Well, we can do that by including some stereochemistry. Let's make the OH bolded, and let's make the chlorine bolded. All right? We're going to put these out. We're going to label them 1 through 4, and we're going to talk about them for a little bit. Boom, boom, boom. Make the OH bolded, and let's make the chlorine here dashed. How about that? Let's make the OH dashed and the chlorine dashed. All right. And what's left? What's the last one?
OH dash.
OH dashed and chlorine bolded.
Yes.
Okay. Are these indeed 4 different compounds? Are these the 4 that we predict we'll have from the 2 ends? Let's start assessing them. First off, how about R and S? Now we put in precise orientations, projections here. It is. You got 2 in the plane, 1 forward, and then the H is back. But we can also have the backbone the same, the OH forward, back, and the H forward. RS here. Oxygen 1, carbon to carbon. Carbon on right or left? We look at what's attached to the carbon. This carbon has LHs attached. This carbon has a chlorine and a carbon. So which carbon is high priority? Need to know how to do that. 2, 3. H is in the back. So what is this? R. Okay, let's do the other carbon. Let's get rid of these numbers. This carbon, chlorine 1. Carbon with O would be 2. Carbon with just H's would be 3. H in the back. So what is this? Also R. Okay, do the other ones. How about that? Everybody get them that quick? Should have. Because if that's R, that's R, as long as the backbone doesn't change. If that's R, what is this one? S, because we switched the projection. So after we did the first one, we cheated. All right? But you understand that you can do that. All right? Again, are these 4 different compounds? Let's label these as 1 through 4 so we can just call them out. Compound 1. What's the relationship between compound 1 and compound 3? 1 and 3. What are their relationships? And don't just say best friends or anything. 1 and 3. 1 and 3 are mirror images. Everybody see it? Are they exactly mirroring? No. Because if I drew this as an exact mirror image, right now these two groups are coming out. The mirror image would be over there, and I hope that the groups would also be coming out. If you stood up and mirrored me, your arms would be pointing this way too. Yeah. But if you came over here and twisted around and tried to superimpose, then they'd be going the other way. We've covered that though. If RR looks in the mirror, what's it going to see? SS. I've got my right arm and leg up. You mirror me. Right, you are left. 1 and 3 are enantiomers. Also called a DL pair. Can we call it a DL pair? Is everybody okay with that? Because we know, first off, we could have started with this. Is this compound chiral? Here you can't really, it's too generic. Let's just start here. Is this compound chiral? We've sort of already answered, well, not really. Because we got to be careful with this. 1 and 3, I agree, are mirror images. But are we certain that they're different? Only if they're different would they then be called enantiomers. We got to be careful about that going forward. Question though, is this compound chiral? Yes, it has 2 chiral carbons. It does. Because this carbon is a tetrahedral and is attached to 4 different things. So is that one. But is it chiral? What does that mean? Is the mirror image different? That's what the question means. How do we know if a compound's chiral? How do you know if a paperclip is chiral? What do we want to look for in a paperclip? Why was the paperclip not chiral but by hand chiral? Plane of symmetry. Where's Waldo? That's a very fundamental question. Does this have a plane of symmetry? Yes, right through it. Does this compound have a plane of symmetry? Are you confident that it does or does not? Maybe if I rotated it. Does this have a plane of symmetry? If it does, then the mirror image is the same thing. Are these really enantiomers or are they the same thing? That's a good, important question. Does anybody have that answer? It all comes from plane of symmetry. Does this have a plane of symmetry? Well, guess what? It can be difficult to see planes of symmetry in projections like this. It's much, much easier to see planes of symmetry in Fischer projections. That's one of the reasons we draw Fischer projections. It's easier to work with. We're going to do a Fischer projection of this. Let's do it. We have two chiral carbons connected to each other. So we're going to have a double crosshair. Let's get rid of this. I'm going to number these 4 carbons of the chain. 1, 2, 3, 4. I don't know if that's nomenclature or not, because in terms of nomenclature, that could have been the 1. I'm not necessarily nomenclature. And here I'm going to have 4 carbons. 1, 2, 3, 4. Thus, the 1 carbon's at the top. If it's at the top, that means the ground is down here. Right? 1 is up in the air, and as we go from 2, 3, and 4, we're getting closer to the ground. 1 is up in the air, and as we go from 2, 3 to 4, we're getting closer to the ground. Okay? Now I'm standing on the ground. So I want to stand on the ground, right? Let's look at carbon 2. 2 and 3 are chiral. Let's look at carbon 2. First off, there is a dash going back. It's the H. We stand here on the ground, look through there, I see carbon 2. What's on carbon 2 coming towards you guys? The OH. So if I'm up here, it's on my left. The OH is on the left. What's on carbon 2 going behind the board? Which if I'm up here, okay, pretend me hovering up here, like the ground is here. Or we can turn this all up. But if I'm up here, what's going behind the board on carbon 2? I'm drawing hydrogen behind the board to my right. I'm drawing what I see to the right. This methyl, methyl 1, methyl 4. If I'm over here, the methyl's going straight away from me. Methyl. Okay? Going straight away from me. It's also going up a little bit. Now this could have been more like this. But if I have if I'm looking straight through here, the methyl is a little bit up compared to my line. That's the top carbon. Let's look at the bottom carbon. Here's the methyl number 4. It's in the plane. The things that are dashed in bold are going to be on the sides, okay? We said that before. The chlorine is dashed or bold. If we're over here, hold on, we don't want to be over here. We actually want to be over here. And look through here. Why do we want to be over here? Because this methyl needs to be going away from us. The methyl is here. Is this methyl, is that methyl down there coming towards me or going away from me? Going away from me. With the methyl going away, which side is the chlorine on? Well, I want to stand with the methyl going away from me. And with the methyl going away, the chlorine is coming towards you guys, and so it is on my right. This is compound 1 in a Fischer projection. Now, when it's in the Fischer projection, you have to trust planes of symmetry. There's only two possible planes. Straight this way, or straight this way. Okay? Is this a plane of symmetry? If I cut right through here, will I have the same on one side as the other? No. Chlorine over there, there's no chlorine over here. The other one, and the one that we'll always look for more often, is right through here. We cut right through here. Is that a plane of symmetry? No, you got to have chlorine above. There's no plane of symmetry here. No plane of symmetry. Since there's no symmetry, what does it tell us about the mirror image, which is 3? It's different. It's got to be. Something with no plane of symmetry in the mirror image is going to be different, just like with a hand. What's the relationship between 2 and 4? Yeah, they're mirror images. 2 and 4 are mirror images, but they're also enantiomers. It's another DL pair. You want to make sure you prove yourself that there's no plane of symmetry here. Okay, what's the relationship between 1 and 2, though? Are 1 and 2 mirror images? No, they're not. The mirror image of RR is SS, it's not RS. Are 1 and 2 stereoisomers? Do they have the same connectivity? Yeah, you got the backbone with an OH here and a chlorine there. OH here, chlorine there. Same exact name. So what's the relationship between 1 and 2? Yes, 1 and 2 are known as diastereomers. Diastereomers are stereoisomers that are not mirror images. It's kind of a default category. Diastereomers have very different properties. Enantiomers, we know all that story, same properties except for PPE light. One rotates one way, one the other, and so we can call it a DL pair. I don't know which is which. Diastereomers. What is 2 and 4? Oh, we already said that. Other diastereomers. We're about out of time. One thing you need to do here. Draw Fischer projections for all 4 of those compounds. And look for planes of symmetry. And then repeat that below with the other compound. Basically, go through this type of assessment with all 4 compounds here. Draw them below all 4 compounds there. The compound below, we're going to find something different. Something called a meso compound. Have a good day, guys.